All right, Unit 8, acid bases. We're on question number 21, so let's get to the questions. Which of the following is the best particulated representations of the species other HO that are present in significant concentrations in the solution at point U in the titration? Let's find the, here you go. Point U, ooh, look at that. Point U is when this thing is incredibly basic. It's incredibly basic, right? So first thing I'm going to look for in these diagrams is OH minus. So it can't be this. There's no OH minus. There better be OH minus. This is when it's completely basic. Wait, here, no OH minus, no OH minus. What the heck? The answer is clearly B because it's the only one that has OH minus involved, and you better have OH minus involved, okay? Because when you talk about bases and acids, especially you're going to be mainly basic when you're past that equivalence point. All right, question number 22. Let's not do, okay? Don't do number 22. Don't do number 23. Don't do number 24. Don't do number 25. And let's go to 26. The reason why is because these are repeats. So let's go to 26. Ooh, interesting question. I've got to remember what the heck. Okay. Oh, this is just a lab tech question, which appear once in a while on the AP exam. I don't focus on them very much just because they're just not that often. A student pipetted 5 25 milliliter samples of hydrochloric acid and transferred each sample to an Erlenmeyer flask, diluted it with distilled water, and added a few drops of phenolphthalein to each. Each sample was then titrated with sodium hydroxide solution to the appearance of the first permanent faint pink color. The following results were obtained. Look at the first sample, second, third, fourth. Okay, so the first sample was lower than the rest, but it was always just a little bit off. Which of the following is the most probable explanation for the variation in the student's results? So why did it go from 35 to 36? And after the first time, the answer is D. The pipette was not rinsed with the HCl solution, and if you rinse it with HCl solution, you get rid of the trace amounts of the base. You got to do that, and it's just not a big enough question, but that is the answer, D. Number 27. A student prepares a solution by combining 100 milliliters of 0.30 molars of HNO2. Now, HNO2 is a weak acid, but this is a weak acid with its conjugate base. Okay, which of the following represents the reaction that best helps to explain why adding a few drops of a strong acid does not significantly change the pH of a solution? In other words, this is a buffer. The answer would be D. This is, again, I don't like that they didn't write double arrows here. Okay, but you have your acid, your weak acid, and its conjugate base. That is acting as the buffer. Okay, a student pours 10 milliliter sample of a solution containing a weak acid and, again, its conjugate base, creating a buffer into the test tube. The student adds a few drops of bromocresol green to the test tube and observes a yellow color, which indicates the solution is less than 3.8. Based on this result, which of the following is true about the relative concentration of those? Oh, this is great. This is a Henderson-Hasselbalch. You have pH is equal to pKa plus the log of A minus over HA. Well, okay, let's go over this. Your pH is 3.8. Your pKa is 4.8. What? If your pH is equal to 3.8 and your pKa is 1 higher, that means this guy right here is equal to, let's say, -1. All right. So now we got to work in the reverse. Now this is where you got to be good at logs. If log of A minus over HA is equal to -1, you got to think about what that means. That means okay, actually, don't try to calculate this. I mean, which you can. It's not that bad. It's like actually 10 to the -1. But if that means that if this number is a negative number, that this number right here has to be less than 1. It has to be some kind of fraction. Like, if you take the log of a number and you get a negative number, then that means this was like 1 over, well, this was 1 over 10. In other words, that your HA had to be greater than your A minus. That's all we really need to know. All right? So what's the answer? Your HA was greater than your A minus. HA was greater than, the answer is A. Now, how do I know that? Why is that A minus? Well, the Na is a spectator. It just goes away. So that's really just your acetic acid is greater than your acetate ion. It's a great Henderson-Hasselbalch question. All right, hey, here's phosphoric acid and its 3 forms. On the basis of the information above, the buffer with a pH 9 can be made by using. Okay, this is kind of like a unique question in this packet as well. But if you have a buffer, if you pH 9, it's going to be 10 to the negative 9, right? That's going to fit right in between these, in between these, negative 8 and negative 13. So the correct answer here is going to be D. A buffer needs to be able to be in the same range as the acid itself. So you would use these 2 items. All right, now we're at 30. Okay, just look at these numbers. Look at the Ka of solution 1. That means this is a whole lot, there's not a lot of product, but there's a whole lot of reactants, right? This one is basically, there is equal amounts of product and equal amounts of reactant, yeah? So this is solution 1 and solution 2. All right, acid dissociation constants of 2 acids are listed in the table above. 20 milliliter sample of 0.1 molar solution of each acid is titrated to the equivalence point with 20 milliliters of 0.1 NaOH. Which of the following is a true statement about the pH of the solutions at the equivalence point? Okay, weak acid, this is basically a weak acid, right? Or it doesn't disassociate very much. And it's a lot, okay, it's not that it's a weak acid, it's that it's a whole lot weaker than this, okay? So if it's a whole lot weaker than that, then that means it doesn't disassociate very well. It doesn't provide a lot of H+. There's not a lot of H+ in acid 1, okay? Meaning, if you combine that with a strong base, this is going to have a higher pH. Acid 1 is going to have a higher pH than acid 2. So first of all, solution 1 has a higher pH, solution 1 has, okay, so it can't be C or D. All right, solution 1 has a higher pH at the equivalence point because C, the top one is a stronger acid. No, this is the weaker acid. So the correct answer is B. Remember, strength in terms of acid is how well it disassociates, not, whether it's going to become more acidic or less acidic. It's actually the inverse of that. All right, now we have HCN being put in water and forming hydronium and Cn minus. You have your Ka there. The equilibrium reaction above represents the partial ionization of the weak acid HCN. A 0.20 molar HCN solution has a pH of 4.95, and then we add 0.05 grams of NaCN added to the solution of that. Which of the following explains why and how the pH of the solution changes? Okay, so if we are going to add some of this, the Cn minus, we are adding some buffer here, yeah? And if we're adding some of that buffer, then it's going to increase our pH, right? Because think of this. You have your HCN plus, or let's just draw your arrow. You have your H plus, and you have your Cn minus. Like this is a abbreviated form of the equation given above. I'm just drawing that too ugly. I got to redraw that. Okay, So if I add Cn minus, what's going to happen? The Le Chatelier's seesaw is going to go to it's going to fall on the right because we're adding Cn minus. So what would it do? It would create more HCN. But if it creates more HCN, this H plus is going to go, these guys are going to go to this side. In other words, your H plus is going to decrease. If your H plus decreases, then you are going to become more basic. If you are becoming more basic, that means your pH increases. So it's going to be, it has to be between A and B, and the correct answer is A. Let's read it. The pH of a higher than 4.95 because CN will disrupt the equilibrium, resulting in an increased production of HCN that decreases the concentration of H3O+. That is correct. 32. Okay, now you have your acetic acid, water, you have hydronium, acetate, okay, all this stuff. A buffer solution is made by acetic acid and sodium acetate. The major equilibria in the buffer system are represented above. Which of the following equilibrium could be used to support the claim that the addition of a small amount of NaOH to the buffer will result in only a very small change in pH? All right, where a buffer is when you have your acid and its conjugate base, and that looks like the correct answer is B. Yes. You have your HA and you have your conjugate base. Okay. All right, let's look at number 33. All right. Acetate buffer solution is prepared by 50 milliliters of 0.2 molar acetic acid 5.0. Okay, so you have your conjugate, you have your acetic acid and its conjugate base. Okay. And a sample of NaOH is added to the buffer solution. Which of the following is correct pairing of the acetic species present in greater concentration? Okay. We just added, okay, so okay. You have acetic acid, and you are going to have your acetate, C2H3O2 minus, and obviously the H plus. Okay. So here's your formula. All right. Now you have equal amounts of your acetic acid and equal amounts of your sodium hydroxide, so this is at equilibrium. Okay. Now you've done what you need to do for a buffer. You got a whole lot of this, and you got a whole lot of this set up, okay? There's a lot of your acetic acid and a lot of your acetate ion, okay? Which of the following, okay, but then you add some NaOH. When you add that NaOH, what are you gonna do? When you add NaOH, you consume, and this is a really bad color, okay, you're gonna consume that H+. That H+ is gonna go away because you got rid of it, so what's gonna happen to the Chatelier's principle? Then you're going to create more of the stuff on the right to get back to equilibrium. In other words, your C2H3O2 minus is going to go up, right? Because the NaOH is getting rid of that. Ooh, I don't know. I'm confused now. Okay, so it says, which of the following is correct pairing of the acetate which of the following is correct pairing of the acetate species present in greater concentration of the pH in the solution after the NaOH is added? So, okay, it has to be between C and D, or I shouldn't do that. It can't be A or B because we know that the acetate is in greater amounts. Oh, you know what? And I think they messed up here. So, okay, if you do your Henderson-Hasselbalch, its pH is equal to pKa plus the log of your A minus, which we're saying this is now greater than that. So your A minus is greater than your HA, like your HA is tiny. So what does that mean? This means this is going to be a big positive number. If your pKa is 4.7 and this is a positive number, then your pH has to be greater than 4.7. But both of these say less than 4.7. They messed up. They say the answer is D. They must have just not written that sign correctly because these are both the same answer. So the answer is D on number 33. All right, number 34. Oh, this was a good question. Okay, you really got to know your Henderson-Hasselbalch here. An unknown acid is dissolved in 25 milliliters of water and titrated with a 0.1 molar NaOH. The results are shown in the titration curve above. Which of the following could be the unknown acid? Okay. I want to, dude, I struggled with this. I was thinking and thinking and thinking, and then I realized, oh, here's the equivalence point, okay? And, dude, sometimes when I don't know how to do a problem, I just move until I figure it out. And then I said, oh, if that's the equivalence point, well, guess what? The halfway equivalence point is right there, 12.5. How did I get that? Half of 25 is 12.25. So this is the halfway equivalence point. If that's the halfway equivalence point, then that sure looks like 3.8. Okay. This is a Henderson-Hasselbalch kind of disguised in a very easy fashion. You've got to know that the halfway equivalence point is when your pH is equal to your pKa. And your pH was equal to your pKa at 3.8. All right, 35. At 25 degrees Celsius, an aqueous solution with a pH of 8 have a hydroxide ion concentration of OH minus of, okay, well, my pH plus my POH is always equal to what? 14. So if this is 8 plus POH equal to 14, POH is equal to 6. Well, then what's your OH concentration? Well, 10 to the negative POH is equal to OH, so that would be 10 to the negative 6. The answer, C. All right, let's go to this next crazy graph. Now, this one you have this one you have a strong base and a strong acid. To determine the concentration of NaOH in a solution, a student titrated 50 milliliter sample with a 0.1 molar HCl. The reaction represented by above, the titration is monitored using a pH meter. Well, where was the equivalence point? The equivalence point, M1V1, was when 50 milliliters of HCl. So you had 50 milliliters sample of NaOH, right? And then you needed 50 milliliters of your HCl at 0.1 molar. I'm just going to, get the cat out of the bag. M1V1, M2V2. This is 0.1 molar as well. All right. At the point in R on the pH curve, which of the following ion are present in the reaction mixture and a concentration greater than 0.01? R, right? R is the equivalence point. That's when you don't have your H pluses or your OH minuses. Your H pluses and OH minuses are at 1.0 times 10 to the negative 7 each. So no H pluses, no OH minuses. You have basically just salt water at that point. Number 37, one student titrated NaOH with 1.0 molar HCl instead of 1.0. He does really, really strong stuff, right? How would the student's titration curve differ from the original? So the original curve was something like this, but that's when we thought it was 0.1. Now he's using 0.1, and that's going to make it go whoop, like really low. It's going to go down really, really, really far because it's going to be super, super acidic. Just putting all that. So the answer, D, the pH far beyond the equivalence will be lower than the original curve because it's using something super acidic. Okay, number 38. Potassium hydrohalate, KHP, is used as a primary standard for determining the concentration of a solution of NaOH by titration. If the KHP has not been dried before weighing, the calculated molarity of the NaOH would be okay, so I want you to think you have KHP plus NaOH. this, if you didn't dry this out, you have the weight of the water here too, right? So this is making this thing heavier. So then we would assume we would need more of this. So it would, if this was heavier, right, then this is heavier by mistake, right? Because there was just actually water that we were adding to it. So your answer is A. The higher the actual value, since the water included is apparent mass of KHPE. That is correct. Okay, number 39. I knew this question was coming. It's been a while. We talked about this on question number 1 as well. In the pure water, some of the molecules ionize according to the equation H2O yields H plus and OH minus. The extent of ionization increases with temperature. The student heats the pure water and records that the measure of pOH at 50 degrees is 6.6. Based on this information, what is the mathematical relationship that gives the pOH of pure water at 50 degrees Celsius? The correct answer here is that, okay, you want to say this, but this is only true when Kw or water is at 25 degrees Celsius. If you really want a good explanation on this, check out my answer to question number 1 in this whole thing. But then if the answer is A, because remember, the H plus ions came from the same place that the OH minus ions came from. So these numbers are always going to be equal. So yes, the pH is 6.6, the pOH is 6.6, but at 50 degrees Celsius, the pH plus the pOH does not equal 14, okay? This is only true at KW as at 25 degrees Celsius. Here it would be 13.2, which is very strange, but it does happen. All right, last one for this section. Number 40, again, okay, so I see a tiny curve there. This is a weak base with a strong acid. All right, B plus HCl yields HB plus Cl minus. Graph above shows a titration curve from an aqueous solution of a weak base with HCl as a titration. Based on the graph, which of the following estimates the pKa of HB? Remember, the pKa is equal to the pH at the halfway equivalence point. Where's the halfway equivalence point? Okay, so if the again, if the equivalence point is at 50, the halfway equivalence point is at 25. That means the number is somewhere around, I don't know, 11. I'm just kind of eyeballing it. The answer is B.